Okay. So let me share my screen. Um, okay. Can you guys see?
Yes.
Okay. So so we move on to the supervised. I kind of give you some big picture of supervised. So we talk about supervised, self-supervised, and transfer learning ensemble. These are the four very useful ones. So far, I just myself cannot find any um, fruitful use application for reinforced learning or adverse learning, but we may keep eyes on that. Maybe you can in the future can find good research questions using that technology. So so some of you guys already know cross validation. So let me just explain the idea of cross validation very briefly, and you guys can check some book. I gave you guys statistical learning that book explain cross validation much better, more details, but just give you some ideas of cross validation, and you can see what's the idea. So basically so basically let me let me draw some, maybe draw some pictures here. Okay. Mm,
Sean, just a quick,
yeah.
real quick specific question. Do you use Python for this?
Yeah, Python is very useful, but you can use R too.
Okay.
Yeah, I use C. My personal preference is C. It's very Asian, like a very old language, but that's my
Okay.
Yeah.
But any of those three will work?
Which one?
Any of those three will work for most of this
Yeah,
stuff?
yeah. Any Java work too. Yeah.
Okay.
Yeah, it just depends on preference. Most popular is Python. Easiest is Python.
Okay.
Yeah, Python is the easiest. Yeah. Okay, so let's draw like a cross validation. Let's say I have a picture. I have a 1 million dog picture. We want to classify what is dog, 1, what is non-dog, 0. So we want to get the classification of dog picture versus non-dog picture. So cross validation means first, human has to label the dog. You get the sample like 10,000 pictures. Human label it. Human label it as a dog with a non-dog. And then what you do is you build a CNN, convolutional neural network, to mimic the human labeling process. So human, let's say human has like human label all these 10,000 pictures as dog and non-dog. So each of the picture, you know the true answer, right? Each of the picture, you know the true answer. So what you do is you split the sample into a training sample and a test sample. So basically you take out like let's say 2,000 as the test sample, and then you have the 8,000 as the training sample. So in the training sample, what you do is in the training sample, you study the human pattern of labeling dogs, or you study the pattern of the dogs. Dogs has 2 eyes, 4 legs, furs, like a cute ears, like everything. So use the 800 sample to study the pattern of the dog features. And then once you build a model, what you do is you use this model to predict the dog or non-dog in these 2,000 sample to check if it's wrong or right. If its accuracy is very low, you go back to tune the model again and again. And I will spend time to explain how to tune the model, but right now, just give you an idea. There's a lot of parameters you can tune for the machine to understand the characteristics of dog. So you go this back and forth, back and forth, back and forth until you receive like a satisfactory accuracy, like 80% or 70%. So basically, what does that mean is the model you build here to predict any dog here should be 80% right. So So that's accuracy. That I don't want to make it too complicated. We have recall rate and accuracy. Let's just focus on that accuracy before we get too complicated. So that's the process we are doing. We tune models. We tune the models using the 8,000 sample to study human labeling process. So this is artificial intelligence because human recognize dog. When you recognize dog, you have some implicit rules there. The forelegs, the furs, the shape. You just don't know. It's unconscious in your mind. So what machine learning do is actually they extract the rules you are using to recognize dog. They reversely recognize this pattern for you using the computational iteration, like repeatedly doing that to get the pattern, the characteristic dog. So that's the idea. That's the part of the AI to mimic your intelligence of recognizing a dog. And the one problem sometimes is for this kind of study, there's one big problem is we call the unbalanced sample. So what does that mean is so we have 10,000 dog picture, right? But what if in these 10,000 picture, only 50 is dog, the rest of 9,950 is non-dog? In that case, it's very difficult to study the characteristics dog. The reason is because the dog picture is a very small sample of the labeling, right? Does it make sense? Does it make sense? Okay, so you have to do a lot of stuff to handle that. So I don't have time to go over that details, but this is something I have to skip. But I just want to give you some challenges we have. The unbalanced sample is the challenge. We have ways to handle that, and the parameter tuning is the challenge. How to tune the parameters back and forth to get the best model, that's the challenge. So these are the common challenges I just want to throw out here. You'll be well with. We always have a solution for that. Just something you need to dig into, and I'm going to skip that, but and you can understand the idea of this kind of process. Basically, it's a repeating process to optimize the way of mimicking human intelligence of recognizing a dog. So that's the idea of cross-validation, and we repeat this many times. So basically, one problem is, what if this 2,000 sample is not randomly drawn? So after you finish this process, you draw another 2,000 sample again to repeat this, draw again and again. So you repeat this many times to make sure this 2,000 sample, test sample, is randomly drawn from the sample. Does that make sense? Does it make sense? Just to make sure this is representative of the sample. So once you have the model, once you repeat this 2,000 sample 10 times and you can get 80% accuracy, what's next? What's next?
You test your model.
Finished. Test model finished. You just have the 80% for the 10 times of 2,000 sample. You have the model ready. What do you do next?
To do out of sample test.
Exactly. So you only labeled how many from the 1 million pictures? You only labeled 10. You have 99,000 pictures. You know, I can't add them up. So you have a lot left for you to out of sample, right? So this is what you do next. Save the label, right? Save the label. So this is the cross validation. Let me clean this. Okay. So what's the difference between the supervised and the self-supervised? So this is a self-supervised machine learning. So the difference is, in the earlier example, human label dark and non-dark, right? The self-supervised means you have the existing label. So for example, here we're predicting stock price. We are predicting stock price in. Can you guys see my mouse? The the mouse. Can you see that? Okay. So you're predicting a stock price over the testing period. So this is the validation sample, this training sample. So basically repeat what I said before, but in a time series way. You use these to study the pattern, and you predict this price. And if it's right, you're right. If it's wrong, you go back to repeat. Once you finish everything, and you use the model to predict the testing sample stock price. So the difference between here and the dog example is dog, human label it, but here the stock price is already available, right? It's already available. So that's the difference between the supervised learning and the self-supervised learning. For supervised learning, normally human label it. Human has the recognition process. The self-supervised learning is you use the all existing label to train a machine. Yeah. So like the price here, the price is existing label. You train a machine. So I just mentioned another, like 10 minutes ago, I mentioned another self-supervised learning to you. Can you guys recall what I said? Like a couple minutes ago, I actually said another self-supervised learning example to you. Any of you can recall? Sometimes I do raise some quiz, right? So just make sure you guys are following me. Yeah. Okay, you see here, you see, this is also example of self-supervised. See, because the cash flow is a label. You use cash flow as a label, use predict surrounding words to predict. So this is the self-supervised example too. You don't have to label cash flow. So it's already there. You just mark it and then use that label to predict that. So this is also self-supervised example. Yeah. So definitely you see the advantage of self-supervised learning, right? You see the advantage. Advantage is save the labeling process. That's a huge labeling cost, right? So so that's the self-supervised. So the transfer learning is I'm talking about transfer learning later on. Let me just transfer learning is the best useful one. So basically you build a model already, and then you use previous model, pre-train the model for your research question. So you don't have to train the model on your own. So for the dog, we already have the model for dog, cats, everything. We have model for recognized computer. So basically, the beauty of the current contemporary world is we have all these pre-trained model. You can already recognize dog, cell phone, everything, almost everything. You can just use their model for your own model. So that's transfer learning. You use the pre-trained model that already capture human intelligence to build your own new questions. That's why sometimes people say, my model is 3 years old, your model is 10 years old, his model is 20 years old. This is the definition of transfer learning. 3 years old model has the intelligence of some pre-trained model. 10 years old model built on the 3 years model, they add more stuff to the 3 years old model. So the transfer learning is the future because we cannot start from scratch. We always want to build on other people's model to build your own stuff. So that's the transfer learning. Ensemble learning, I will talk about ensemble learning later on. I'm going to skip reinforced learning. I think for the sake of the time, this is something you guys can follow up later on, or we can. So I have to skip a lot of technical details and the stuff here. Because I want to give you guys the big picture of what is going on, and for this technical part, we can find some other occasion to discuss. So this is some model horse race I want to share with you guys. Can you guys see the screen? Let me see. So this is the horse race of the model. So you can see that this is one of my project. I horse race CNN 3 layers, 1 layers, 2 layers, and logistic regressions, gradient boosting, XG boosting. So I horse race. So this is the benchmark we use. So we have the accuracy. We look at the F1 score. So I'm going to skip this because you can just check the this is basic concept you can check online. We get the best one, but I want to point out is so you can see that we have a linear model, non-linear model. So you can see that if linear model is better or nonlinear is better, it helps you to select the model. If nonlinear model is always better than linear model, you want to stick with linear model. If linear model is better, you want to stick with linear model. And so you have a linear, nonlinear, and you have a lot of stuff you can choose. You can choose different model. In each model, you can choose the parameters. For example, some of you ask more layers. The more layers does not necessarily is better. You see the CN 5 layers, it has worse performance than the 3 layers. Because why is that? That's the nature of the data. The 3-layer CN can capture the data pattern better than the 5-layer CN. That's what we want. That's what we want. So how do we know the 3 layers is better than 5 layers? Cross-validation. Do you guys still remember the dog we repeat back and forth, back and forth? So we repeat that many times until you get the best layer parameters to capture the feature of the dogs. So if you ask me ex ante, do I know this is 3 layers better? I don't know. But ex post, the 3 layers does better. I can have an interpolation because the CN 3 layers means 3-way interaction. So the 3 interaction better captures data. So we can interpret that, but in ex ante, you have to have the computer to find the answer. So some of you was asking like difference between the OLS and the machine learning. I give you guys like a very simple example here. So if you optimize the dot distance to this line, that is OLS. Make sense? Like each dots, if you minimize the distance to this line, the black line, that is OLS. Okay. This is the simple way to twist OLS to machine learning. This is a support vector regression. So what people do is you are not minimize the distance to the line. You are minimize distance to this area, So for example, you guys see the 2 dots here, the blue dots and these dots. So in a traditional OLS, this will has some error distance, right? But in a support vector machine, this will be considered as perfect fit because it's in the area. Does it make sense? Okay. The question becomes, how do you know what's the best area? What's the best fuzzy area for you to get the relation? If the area is too huge, then maybe it doesn't make sense. If areas is too narrow, it will be exactly become OLS. Does it make sense? So how can we get the best distance? What's the best? This is called the bandwidth. This is an important parameter in the SVR. So how do you determine what's the best bandwidth for this case? How we do so?
So you combine the bandwidth to your objective function.
Cross-validation. Okay. Do you guys remember like the dog case? The 8,000, we go to the 2,000, we back and forth. So you basically you just do the parameter training. You train different parameters until you find what's the best bandwidth, and you stop. Does it make sense? But there's so many bandwidth. How can you, which one you should start with? Which one you should, like so many options. How can you try? So this is something you need some computer science expertise to determine that. That's how you come up with this. That's where. But for normally, what you can do is you can fix. There's some fixed parameters for this, like bandwidth. There's some fixed parameter. You can just start from the fixed ones, and then you can get the better one. So that's why I was saying the parameters training is important. That's why the cross validation is important. Yeah, does it make sense?
So about the neural net, so the choice of layers is a purely empirical question, and you always brute force try different layers for this kind of questions. Is that?
Yeah, it's too many parameters. You don't know ex ante. You don't know. But the more model you run, you have experience. Like for example, I know this one CN will work much better than others. So the more experience you have, it saves time on the model selection. And sometimes for some parameters, I already know the parameters should range from what to what. So experience can help you to reduce the selection process. That's true. Yeah.
What are you predicting here?
Earnings.
Earnings. Okay. So I think for Gu, Kelly, and Xu 2020, where they use firm level characteristics to predict stock returns, the best performing neural net is also about 3 layers one, I think.
Yeah.
Um,
So why CNN here? So why Hank was asking why not use neural network? Why not use CNN? So let's go over some basic concept here, so you guys can see what we're talking about. So this is the let me enlarge this one so you guys can see. So this is the typical neural network model. So what neural network, you can see that this is a process of dimension reduction. First, you get all the pixels out, and you do the dimension reduction, you get the layers, and you do the dimension reduction, get the corners, and you do the dimension reduction, get the objectives, and then you get dimension reduction, get the cars. So when I say dimension reduction, you can understand it's like extract useful information from the noisy data, like voluminous data. You can just understand the dimension reduction in that way. So so here, this is the neural network, right? Neural network. So you can see each layer help you to reduce. So each layer help you to get the information out, right? So the first layer to get the layers out from the pixels. The second layer to help you to get the corners from the layers. So each layer help you to reduce the so high dimensional information to low dimension. So basically each layer helps to extract useful information and then take out the noise ones. So this is a very the picture to do the neural network. So the more layers, like sometimes people have some understanding, more layers the better, because the more layers you can have more dimension reduction. So that's sometimes people believe that. And so let's see. So let's see what's the difference between the neural network and the convolutional neural network. So let me ask you guys a question. For the sunglass, it's sunglass and the head. Does the head help us to recognize the sunglass? Does the head help us recognize the sunglass? The two does, right? Does. Okay. So we have a building here. We have a chair here, the two-person chair here. Does the chair help us to understand, recognize the sunglass? I don't think so. I don't think so. So this is called a local dependence. So what does local dependence means? You don't need the whole picture to understand the sunglass. You need the local information to understand the sunglass. Does it make sense? Okay. The traditional neural network doing is they will scan the whole picture to get the information as an input to understand the picture. That's the traditional neural network. But what I'm talking about here is if you scan the whole picture, there's so much noise information here, the trees, the buildings, you would just make the recognition of the sunglass very difficult. Does it make sense? How should we do? If we don't scan the whole picture, what should we do? What should we do?
You put more weight on the closest parts to the
how exactly we put more weight? The idea is correct, but how exactly we put more weight?
You mentioned the convolutional network.
Yeah. How exactly convolutional neural network do?
I don't remember. I don't know much about convolution.
What would you guys do? Just out of like just.
Could you separate them into layers, into the layers you were talking about?
Okay.
Local.
So what convolutional neural network do is you scan local picture. You scan here, you scan here, you scan here, like you rolling scan. Each time you scan it and get information, you scan local. So basically here, when you scan here, you can scan here just the local head, and you can just rolling scan until you scan a whole picture. That's convolutionary neural network. That's the definition of convolution. So let's look at the big picture here. So so look at here the picture. So the dog here, right? So dog. So what you do is you scan the local here, and you scan local here. You keep scanning until you finish the whole picture to get and you understand the picture. Okay, the several things that I want you guys to understand the parameter tunings. One thing is how do you know what size of the picture you should scan? Like this is called a kernel size, okay? When you run the CNN, the parameter is called a kernel size. So how do you know what's the best kernel size you should have? How do you know?
It probably depends on the overall picture size, maybe.
Possible? Yes, that's good. But how can you decide? Like here, you can human tell, no, this is good panel size, kernel size to scan. Here, this is good kernel size. Human can easily tell. So how can you let computer tell?
Use validation sets.
Cross validation, okay, cross validation. So you try different panel size, you try and until the get the best recognition for you. And so this is the one parameter. So I was talking about you guys how to tune the parameter. So this is one important parameter you guys tune. Okay, the kernel size, like how to determine the kernel size. You have to use the cross validation, repeat back and forth until the machine find the pattern of the size of the kernel. Yeah. Another one is, yeah, go ahead.
How do you know when you have the best?
Because you have labeled the dog, right? You remember the 2000 pictures, you have the dog. So whatever can capture the most accurate dog, then that would be the best.
But in terms of most accurate, it's not going to be 100%. So what is your cutoff then for most accurate?
I mean, you can see
you
can see here the accuracy though. If I got 68, then 61, I know the 3 layers will be better.
So out of the layer test that you run and you 68,
I can change the parameter to the kernel size, right? I can say this is like a 3 size kernel, 1 size kernel. If the 3 size kernel is better than 1 size kernel, now we'll choose 3, right?
Yeah, so it just depends on the test that you do.
Right, depends on the accuracy, right?
Yeah.
Yeah. The accuracy is you know the answer, right? Because in the test in a test sample, you label the dog, right? You label the dog for the 2000 sample. You know which is dog, which is not dog, right? So let's say here, if the size 3 can predict a dog better than the size 1, and you know the size 3 is better, right?
Yeah, I guess what I was asking is, so how do you then know if there's another amount of layers that would give you 70%?
So that's why you keep running. You keep running many times until you get a curve like flat.
I see. Okay.
That's why we need like tons of computational power to get that. Yeah.
Okay.
Does it make sense?
Yes. Yeah.
I have a question. So
Yeah.
for normal neural nets, I think the first layer also get the local part of the images, and then the other part of layer sort of look at the combination of those previous layers, right? So how does that differ from the convolutional one?
Yeah. Can you tell me?
Uh,
I think I have explained that. Can you tell me?
You said about the edges. You look at the edges and contours. Is that the different way to look at the part?
So the conventional neural network depends on is full connected, not full connected. It's full connected, then the scan is the whole picture. Then every interaction will be considered. Like sunglass will be the trees will be you will consider interaction between them. The buildings will these are noise. We don't want that. Okay, these are noise. So the full connected neural network, do you get all the interactions, even the distance interaction they will consider, but we don't want that. That's why we do the local scan. When you do local scan, this one and this one will not be interactive with each other. Does that make sense?
Okay, so the interaction will be mainly local, will not be about the two distant parts. I see the point. But this is about images, right? If you think about predicting continuous variables like returns or earnings, your input variables are, say, firm characteristics. Those are, you don't have a physical distance between those variables, right?
Excellent. You have a solution for me?
No.
Then how about wait for my discussion? I will discuss about that.
Yeah.
Okay. But just want to repeat what Hank's point is, if you use the full connected neural network, all the long distance interaction will be all considered, but that's noise. We don't want that. That's why we want the local scan. The local scan will only consider local interaction. Yeah. Okay. So we have parameters. We have parameters like what? We have parameters like a kernel size. And another parameters we have is how much you move. Like for example, you can scan, like you can, next one, you can move from half, you can move like a whole here. So how much you move for between the first scan and the second scan, how long you want to move. That's another parameter that you need to tune, right? And the third thing is the filter. Like when you scan this one, what filter you use to scan? There's tons of options. You can scan a linear, non-linear, and so I'm going to skip that. Okay, I'm going to skip that. So these are the, so my point is there's so many parameters for you to decide. So how you decide? You have to, like I said, you have to run until you get flat curve, and you can get the best model to capture the dogs. And these parameters and the details, you guys can just do some research on your own, and or we can discuss later on when in other cases. And so let's go back to Hanke's point. What if it's numerical data? So basically, if I believe right, is here the order matters, right? So when you local scan, the order matters. You scan here, you scan here. The order of the pixel matters. But for the numerical data, there's no order. So for example, so look at here. So if you scan the first two, let's say the kernel size is 2. What does kernel size is 2 means? If you scan the 2 variables up, can you guys see the screen? Can you guys see too small?
It's okay.
That's okay.
Okay. So if you scan the first 2 variables, so and you scan the next 2, so if the kernel size is 2, my question is, can you ever get the interaction between the forecasting value and the experience general? Can you ever get the interaction between the two? So basically my point is, if it's a local scan, right? You only get interaction between these two, and another local scan, you get interaction between these two. So for the variables that are far from each other, like forecasting value and general experience general, do you ever get the interaction between the two?
No.
Same here, right? If you do the CN, if you use local scan, did you ever get the interaction between the building and the glass? Did you ever get that? If you use local scan, did you ever get the interaction between the building and the sunglass? You don't, right? We intentionally do the local scan, so these two interactions will not be included, right? Does that make sense? But the picture, good thing about pictures, it has an order, right? This is like it has order. So when you scan, you know the order you can scan. But the problem here is, if you scan like this, if you scan this, the problem is, how do you know the order? Like, how do you know the order? Like, how do you know we should present the variable in this way? Because the order matters. If you present this way, the first two interaction will be incorporated, but the forecasting value and experience general, the interaction will not be incorporated. So the order of presenting this variable will be important. Because, does it make sense? So how to determine?
You need to manually order the input variables.
Exactly. We have to decide what's the best order, because the picture it has order. It already has a natural order, right? But here, if the order is wrong, then you get the wrong order. You have to scan, because this one is the right order. You scan the local, you get the right order. If the order is wrong, you scan the wrong order. So you have to determine the order, right? Does that make sense?
Yes.
So how we do so?
Well, I can think of an example like firm characteristics. You put them together, then you have like macro variables like GDP or stuff. You put them together.
Mm-hmm.
Sean,
so-
can I ask a clarifying question here?
Yes, yes, yes.
So input is a 10 times 1 matrix. What about 5 times 5? We don't need just a vector, right? We input a matrix.
Here,
Yeah.
one more time.
So here the input is a vector, right? There's 10 element vector.
Yeah.
Can we input a matrix? So for a vector, you have order, right? For a matrix, you have other interaction, right? We have more orders in the matrix.
Yeah, the automatically generate the interaction in the second layer.
So not
So when
first layer.
Yeah, yeah. In the first layer, the layers they automatically generate the interaction. Like look at this picture. You see, when the dots are connected, you see this one, this one, and this one. They both point out to this neural, so the interaction will be considered here. And you see this one, the arrow point out this, so the interaction of these two will be considered here. You see that?
Yeah. Yeah. So I just want to make sure. So the input is just a vector, right?
Yeah.
So can you cross-validate the order? So I mean, so you make. So I think you horse race all the orders and then you train them and then see how the accuracy or precision.
Good. Can you give me the
Is that right?
combination? Can you give me the combination? Like if you have 10 variables, how many? What's the all the possible orders you have? Can you give me that?
I mean,
Close to 1 million.
yeah, that's a lot.
And each time you take like 2 days to run, like that's 1 million times 2 days. Right.
So that's why you need a good computing power for that.
But that's
I mean,
too much computing power. That's
okay,
wasting of computing.
okay.
We need to do something, you know. We need to do
Okay.
something. Yeah. Yeah. I mean, with computing power, it's 2 days. With computing power, it's 2 days. Yeah, and it's 1 million times 2 days. Then I mean, we have to finish project. We have to graduate, right?
Yeah. So
Yeah.
so you're saying that the cross validation is kind of right idea, but you're asking like how are we gonna put the orders, because all the cross validations takes a lot of time, right? So
Yes.
the matter is
Yes.
how are we gonna choose that order?
Exactly.
Okay.
Exactly.
That's the researcher's subject, right? Like that's our like judgment going on.
So what do we do is if it's 10 variables, this is about close to 1 million combination too much, right? So what we do is it's like Hank says, we think that maybe some variables, their order between them, it doesn't matter. So we group them. We group the 10 variables into, this is a bad example. We have more than 10 variables. We have more than that. We group the 10 variables into 4 groups. So how many combination we have for 4 groups? Combination of order, how many for 4 groups? 24, right?
24, yeah.
Yeah, so 24 is easy, right? Cross validation 24, 2 days. You say 2 days per one, 48 days, we're done, right? Yeah. So what we do is we assuming there's a between group doesn't matter. So we break down to 4 groups. We only get the combination of 4 groups to determine the order. So one question you have for me is, how do I know the order, the group is right? What if you group another thing? So we manually group to reduce the dimension from 10 to 4. What if we did a wrong group? Right? How do you make that right? So what we do is we check the in group. So if the group is correct, then within the group, the order should not matter. That's what I found. Does it make sense? If we group them right, the order between the group shouldn't matter. That's what we found. If we group them wrong, then the within group should matter. So that's how we reduce the dimension for this case.
So the placement of the groups you're saying doesn't matter. It's the groups themselves that matter.
Yes, the cross group order matters. Within group order does not matter.
Okay.
And we validate that. We found the within group order do not matter. So that means our grouping method is correct. Does it make sense?
Right. It makes sense.
Okay. So so I'm going to skip some of the stuff and oh yeah, this is, let me see. So yeah, this is parameter tuning. So you have to tune the parameters, but there's always efficient way for you to tune, like for example, grouping them. And so you have to make sure your judgment is right. So like I said, I grouping them, I get the best, but you can challenge me. How do you know your grouping is correct? So I have to validate that. I have to validate them in some ways to do that. And so this is like you have to do it many times, like until you get the best one. And okay, this is some of you guys asking me, how do you get the weight for any of the feature on the in the neural network? So how do you get a weight? So easy way is, let's say you have the, let's say in this case, let's say you have a so in the Shou Chen's paper, so they have like about 100 input. So you drop one and see how performance go down, and use that to calculate the weight. So it's like OLS, like you have like 100 variables. You drop one variables to see the R square decrease how much, and use that as the weight for the dropped variables. And you repeat this 100 times, you can get the weight for each variable. That's what we do to get the weight. So going back to Hank's question, we do have some coefficient, different coefficient for neural network. This is go back to my earlier point. This is our business research should do. We have to interpret the model in a new way. So another way is you can add an attention layer. If you add an attention layer to neural network, you automatically generate a coefficient and the weight. So this is another way. So you don't have to drop this. You just add an attention layer to the neural network. They will give you the weight on each feature. And then the last one is gradient descent. So basically, you get the partial derivative to get the partial derivative, because each variable has an objective function. You can get the partial derivative from the for the variable, and you can use that to get the weight. So you have to do calculation on that. I do not recommend this. This is too much. I think the first two are more easier. Yeah. So this is, you can get a weight. You can get a weight. Yeah. And then
You're right.
Yeah.
Quick thing. So in Google, I think in Google, Kelly and Xiu, they didn't ex ante assign weights. They use equal weights for the reduction of R squared to measure feature importance. They basically use that to compare across features, which input variable is more predictive, right? If I remember correctly.
Yeah. Yeah. Correct. Yeah. Okay. So this is ensemble learning. So I'm going to skip ensemble learning too. So the idea is you use different machine learning, you combine them together to get the best machine learning model. So basically, so CNN is good at feature selection. Basically, CNN is good at local scan, local interaction to select the best X for you. That's CNN. LSTM is good at time series data, and gradient boosting is very good at nonlinear. So each machine learning model has its advantage. You combine them together, it's called ensemble learning. There's two ways to combine. The one way combines, you get output from each model and you just combine output. The second one is you get the feature from this, like process the feature from this model. You combine output and feature. So there's different way to combine the machine learning model. The output way is very easy. Just each model give you an output. You just combine them, average them, median them. It's very easy. So feature one is the model not just give you the output, it also give you process the feature. You get both the feature and output to ensemble them together. So that's the ensemble learning. So so I'm going to like I said, I'm going to skip this, but you guys know the idea. Like ensemble learning for me always can improve 5%, you know, accuracy. Like every time I try ensemble, it's just like teamwork, right? You know, I just work on my own, I just get 70%, but I got team together. I mean, with Vivian, I got 100%, I think. Yeah, so it's ensemble learning, just kind of teamwork. Yeah, but exact details, you just remember this output ensemble and feature ensemble. You can check, or we can talk about details in other cases. If yeah. So let me just give you some examples of other stuff. I do have to go. I think you guys finish at 1 p.m. right? 1 p.m. For me it's 1 p.m. Okay. So so let me just quickly go over some examples so you guys can so we talk about different type of research, right? You guys know now the first one is easy, right? Just get the pre-trained package, word embedding, blah blah blah. You can do that. This is not even, you don't even need to know machine learning techniques to do the stir type. So the second one is a little bit challenging, and so we talk about this. So I'm going to skip this. So let's look at this example. So you read this sentence: undeterred by the bad weather, we have experienced great sales.
Can you share a screen? We are still seeing the PowerPoint slide.
Okay, let me do that.
Yeah.
Glad. Otherwise, I will. Okay. How do you know I was looking at the other slides? How do you know?
Because you are talking
You were
about
reading
the,
a sentence.
yeah, the
Oh,
sentence, and we
okay, I
don't
see.
see the sentence.
I
of
see.
the-
Okay.
Yeah,
Excellent.
machine learning, we do the training.
Excellent. Okay. So let's look at this example. Okay. What machine learning can do, what the bag of words can do. So read this sentence. Undeterred by the bad weather, we have experienced great sales growth this quarter. So just count the keywords. Bad is bad negative sentiment. Great is one positive sentiment. So the sentence to you, if you use bag of approach, is that neutral to you? Use bag of approach. Okay. But for human read it, the bad weather, the bad shouldn't count to us, right? What should count should be the sales, great sales. So human reading is more like focus on the great sales. We should ignore the bad, but the backwards approach, because it doesn't have the context, they will just consider bad, count great. So it's neutral for backwards, but to human, it's not neutral, right? Humans think this is positive. Does that make sense? Okay, so what do we do? What we do is we need to know the bad is modifying value, and the great is modified sales. Yeah. So the bad weather and the great sales. So one is negative, one is positive. So we have to ignore this because this is non-performance related sentiment. This is a performance related sentiment. So we have to focus on the great sales. Does it make sense to you guys? Okay.
Yeah.
So okay, the question here is, how do you know which word modify which? Here you know human read, you can know bad modify values, great modify sales. Human read can tell that. How can you let machine know? If machine know bad modify value, then you'll be good, right? You should get the accurate sentiment. But how do you know how exactly which word modify which word? How can you let machine to tell it?
Based on physical location, you can do local scanning maybe.
Okay, let me tell another example. I don't think this seminar is useful. How can you tell in that case? You see my saying? I don't think this seminar is useful. In that case, don't negate the seminar is useful, right? So does it make sense? So how can we, how exactly? So let's look at an example here. A double-digit increase is not an unreasonable goal. So here, if you just do the keyword search, it's unreasonable. It just just one negative sentiment, right? The expose is another one second. So if you keyword search, it will be 2 negative sentiment for the sentence. But when you human read it, not unreasonable, is that negative or positive? When human read it,
It's positive.
Positive, double negative. Yeah.
yeah, it's positive, right? And here, the exposed notifies the countries and regions. So the exposed shouldn't matter that much because this just the subject is countries and regions, right? So overall, this should be the positive sentence, but the machine, the keyword search will be counted as a 2 negative. Something's wrong, right? So the point here is we don't know which one modify which. If we know the not modifies unreasonable and the problem is solved, right? If we know the exposed modifies the let, modifies the country and regions, then the problem also resolved. So the problem here is we don't know which word modifies which word. If we know that information, we can handle this all the sentiment in a more accurate way. Does it make sense? So anyone can tell me how we can teach the computer know which word modifies which. How do we let computer know the relation between any keywords? Because some words have no relation. So increase and increase and special, these two doesn't have any meaning relations, syntax relation, right? The note modifies unreasonable, but not any words has a relation. The increase has no relation with countries, right? So how do we let computer know the syntax relation between any two words? Either they have relation or don't have relation. If they have relation, what type of relation? So how do we let the computer know that?
Maybe you have to train the learning process based off of how the information that you want it to then analyze. So for example, this is what people say. People say these not an interesting goal. So maybe you use dialect text or something to train the learning.
Good.
To get used to that sense of speech.
Good. Excellent. So what the NLP, what we do is we have the human to label this. Like there's a 91. We define 91 syntax relations. So for example, subject, object, like a verb versus adjective. So we have like a 91 type of syntax relation between any words. So what do we do is we have human label 3 million past the text, and then this is the training sample, right? So basically we have the information, human label it. Human has the intelligence. So what do we do next? We have the 3 million training sample, human labeled for the 3 million words. We know the relation between any words. We know the relation between any words for the 3 million words. What's next? What's next we should do? What's next we should do?
You train the sample, then you validate them.
That's what we do, right? We split sample into test sample and training sample, and then we do the parameter tuning. So this is a new network we build on. So we repeat back and forth. So the final accuracy is 92%. So basically, if you have a human to recognize the relation, the model we have is 92 accurate with human labeling. It's not 100%, it's human 92. So some of you said, why you stop at 92? Because that's the best we have. That's the best we have. That's why we stop at 92. Yeah. And so this is a repeating process. So this is AI. This is the AI. So basically human label this all the relation, and then you mimic human intelligence of recognizing these syntax relation between any two words. Even if it's not 100% mimicking, as long as you have 92% mimicking of human intelligence of recognizing this syntax relation, it helps you to save a lot of RA's life, right? Does it make sense? Yeah. So and also it's open to the new large scale of computation, right? It's not just, sometimes it's not feasible for human to do that. So yeah, so that's one example we see. So what machine learning can do, what bag of words can do, this is example, right? If you use bag of words, you get some errors. If you use machine learning, you can get the syntax relation between words, you get a better one. So this is what earlier example I would give you guys. So yeah. Yeah, thank you, Michael. Thank you. So so what do we have here is so yeah, 92% of accuracy of human labeling. So and we use so the function is activation function. So I didn't talk about like neural. Each neural you have an activation function here to do the dimension reduction. So basically you put so how exactly why this kind of information can be reduced to more useful information. How exactly can be reduced? So each circle is called a neural. In a neural, you have activation function. The activation function can help you to screen out useful information for the next layer. And you ask me what kind of activation function we should put in, my answer will be, there will be some general common used activation function, but you can also tune it. You can also try different ones. Yeah. So that's the, does it make sense? Does it make sense to you guys? Okay. So can anyone tell me what's this?
This is X-rays
Of what?
of chest.
Of lens, okay. So some of them is COVID-19 positive, some of them is COVID-19 negative. So some is like we cannot tell which is positive and negative by just, I cannot tell any difference. But the reason I put the example here is during the last year March, like 2020 March, we are short of the doctors who can actually tell the CT and the X-rays here. So the machine learning can do this. I didn't do this. This is some technology company did this. So basically the machine in 20 seconds can tell which one is positive, which one is negative. So how exactly they can do so? How exactly they can do so? The reason is because we have a large training sample, because the doctor actually train them. Doctor has a lot of training sample, which is positive and negative. So with the large training sample, the machine has the 96 accuracy of mimicking doctor's judgment. So basically, since you have the large training sample, the machine can easily catch up, mimic the doctor's intelligence of recognizing positive COVID-19 versus negative COVID-19. So it saves a lot of life, it saves a lot of life.
Is this
So the,
simply, oh, sorry,
go
is
ahead.
this simply a two-step learning process then? Is the first learning telling the machine to say, if there's a spot on the lungs, identify that, and then is the second learning, then that spot is then COVID-19, or is it all one?
All one. So you
Okay.
basically you give like an example I gave you, like you have 10,000 pictures, right? You have like you have a 1,000 is positive, 9,000 is negative, right? So machine will train until they can predict the accuracy, 60% of accuracy to predict the positive ones. Does it make sense? There's no step. There's no step. It's like the step, you can do step only when you get a very advanced level. Like when you get advanced level, you can break down, like say ensemble learning, you can break down that into like you can predict local and then use ensemble everything together. At a very advanced level, you can do what you said, break down into the steps. But at a very beginning level, what people do is you just predict positive or non-positive. But in the practice, you are right. We like I said earlier, the order, we always can break down into local task, and then we get the ultimate task, right? So in the practice, we do that. But this is a case by case judgment. This is case by case judgment. That's why I don't do machine learning in health insurance, because I don't have the expertise, right? But for the finance and accounting, I can do, because I know how to break down. I know how to break down the task into small tasks and assemble them together. So in the finance accounting, I can use my computer science and business expertise to build a customized model. But you want me to do, if you want me to do this kind of model, my solution just do the positive and negative, because I don't know how to break down. I don't know. Yeah. Yeah. So yeah, so going back to how you can get the best model for the so there's only two ways. One is you have large training sample. Another one is, you, like I said, you tune the model millions of times, you get the best parameters. In this case, what we have is we have the large training sample, because at that time we have millions of cases already. So the training sample is large. It releases the pressure on the parameter tuning. So basically, another way to put it is, if the training set is so huge, you don't need to really tune the parameters so many times, because it's very easy to get a pattern from the large training sample. So so does it make sense? Does it make sense? Yeah. Okay. So so this is the project I'm doing right now. So I'm extracting production pictures from the company, and I extract the information which can affect the stock price. So I also use the machine learning to extract the useful information to measure the firm safetiness and the expansion plan and the future expansion plan. So this is the what machine learning can do. Again, I use label. I use RA to label first, and then use CNN to train the model. The reason I use RA is there's no existing label for me. I have to use human intelligence first. And I mimic my RA's intelligence of recognizing useful information from the pictures. And this is also a concept of the transfer learning. So you see this kind of the track, you see the beams, you see the station. I don't have to train this on my own, because I built on the ImageNet. ImageNet have all these small subjects built already. Does it make sense? So ImageNet have already recognized all the small subject. So what I do is I build on the ImageNet, and then I can recognize the useful information that is unique to me. So this is a concept of transfer learning. You don't start from the scratch. The house, the truck, the land, the sky, all this has been recognized, has been trained in the previous model already. I build on this pre-trained model to train. This is the construction side, and that's what I just want you to know, the transfer learning. You guys can use that. So far it's free. I don't know when you will be commercialized. Once you commercialize, that's a different issue. But right now it's totally free for you guys to use. And so any questions so far?
Right. Can you go back to the CNN parts?
CNN part?
Yeah, the convolutional neural net.
Okay, I have to switch the slides.
Just the previous. I think the previous one is good enough. Previous slide.
This is yeah. Okay.
Yeah. So we talked about the order of the inputs, and that's mainly for the convolutional network, right? Because it does the local scanning. But for the common network, does the order matter? Because
what do you mean common network?
Yeah, the ordinary neural network.
So this is your judgment. This is your judgment. Like when we try whether it has local interaction, this is when you have to discover. Mm-hmm. There's no standard answer for that. That's how you have to see whether there's a local interaction in that data or not. This is a part of model selection.
Mm-hmm. Okay.
There's no unique answer. For example, that one, the example I gave to you at the beginning, we don't know this has a local independence. So we try the conventional neural network, we try the convolutional neural network, and we find convolutional network is better. We know, oh, there's a local independence there. So we dig into that. We dig out all the local independence. So you try two models, and which one performs better, it gives you the answer. And then you have to dig into where is the local dependence? We have to dig into that. Does it make sense?
Okay, so you first try both of them, then you look at the, say, in sample R square or out of sample R square. Then
There's
you
no
say,
R square in the neural network, Hank. There's no R square. Okay. There's only loss function. Yeah. Yeah.
the or in mean absolute errors or whatever.
Okay. Okay.
Right.
Okay. Yeah. That's right. That's right. But
Cool.
the thing is it's not trying two models is first step. Once you find one model is better than the other, you have to figure out why. That's most important one.
Then you go back and interpret.
Yeah,
After
you
you
have,
see the results. Okay, I
yeah,
see.
you have to figure out why. Because if the CNN better than neural network, that means maybe there's some local dependence there. But you cannot just tell people, oh, there's local independence. You have to dig out what exactly local independence. You have to tell people. You have to show people. Otherwise, people will tell you, yo, you just wrong different model. You just show this is better. You have to explain what kind of local dependence CNN can capture, but neural network cannot capture. You have to exactly show people. Yeah,
Okay.
that's the challenge I was talking earlier, right? Yeah. Yeah.
Okay, thank you.
Yeah. Yeah. So just a simple summarize for the textual data, you need to first you crawl the data. Crawl data is relatively easy, and you can do keyword search, and you also can do the neural network to do that. And we talk about the example, right? We talk about the example, and we also talk about the frequency-based embedding, word embedding, and the sentence embedding, right? Do you remember frequency embedding? We said it's bad, right? It's bad. The cosine is very, very bad. Word embedding is better, right? But sentence embedding is the most advanced we have, right? So different embedding. So image data, you can use ImageNet, blah, blah, blah to do. And so I just want to emphasize always find the question first. Do not try to sell advanced technology, because if it's technology-driven paper, people will always challenge you. And if you use technology to answer some unique questions, and will be good start. And also interpretation of the question, like Hank was telling me, which is good, is bad. It's not about which model is good. It's about why this model is good. So you have to answer that part. And I want you guys to go back. There's some pre-trained model here. The Google Birds is pre-trained. ImageNet is pre-trained. OpenAI. So far, this is the most difficult one. So this one may be too much, I feel, for you guys. But these first two, I think, is reasonable. And if you use neural network, you can start with Keras. Keras is pre-built neural network. It's most easy to use. If you want more flexibility to tune a model, you can use TensorFlow. And the PyTorch, I think you can just leave them alone, because it gives you more advanced options. But I think for us, most of Keras and TensorFlow will be sufficient. That's some pre-trained package you can use. And yeah.
What's the difference between Keras and TensorFlow? I think previously I used the scikit-learn machine learning models in TensorFlow. I didn't know Keras.
Keras is built on the TensorFlow.
Okay.
Yeah, it's just an interface built on TensorFlow, make it more friendly for you to use. Yeah.
Okay.
Yeah.
Okay, I see. Thank you.
Yeah. And so just summarize with the challenge here. You see people will always ask you, why this technology, why CNN, why not neural network, why not OLS? And I want to put the focus on the economic theories, and also make sure, if you want to do this, make sure your technology understood by non-computer science major. And again, if you guys interested, go to the conference I organized with Baozhong, and we are going to host another conference, probably, I don't know when, but if you guys are interested in joining, you can follow up with me. If we have extra spots, I may sign you up. If I don't have extra spots, we'll always keep in touch. You know, sometimes if it's online, I definitely can get a spot for you guys. If it's in person, we don't charge any registration fee. We don't, so because we have some limited capacity if it's in person. So yeah, just keep in touch. Let me know when I can be helpful. and I have 8 minutes just for you guys to raise questions or farewell or whatever